In this lesson, we'll be looking at solving systems of equations using graphing, substitution, and elimination. A system of equations is a collection of two or more equations, each containing one or more variables. A solution to a system of equations is an ordered pair that satisfies all equations in the system. For example, determine whether or not the ordered pair 5, -3 is a solution to the system. To check this, we want to make a substitution, and we really need to check both equations. We can't just check one of them. So we'll test the first one, 2x minus 5 equals 13, and we're going to plug in 5, -3. So we have 2 times 5 minus -3, and we're asking, is that equal to 13? 10 plus 3 equals 13, and that is a true statement. So we're good there. But we need to also check the other equation. We can't just check one of them. We need to check both. So -4x minus 9y equals 7. We'll also plug in the 5, -3. -4 times 5 minus 9 times -3. We're asking, is that equal to 7? We get -20 plus 27 equals 7. 7 equals 7. That is a true statement, which means that 5, -3 is a solution. So since that coordinate worked for every equation in the system, we can verify that it is a solution to the system. So that's basically how you check your answer, or at least one way to check your answer for what we're about to be doing. There are 4 different ways to solve a system of equations: graphing, substitution, elimination, and matrices. We'll look at one graphing and we'll focus on substitution and elimination in this lesson. We'll save matrices for another lesson. To solve by graphing, we're going to graph each equation and then see where they intersect. For example, let's look at this system. We'll start by solving for y, isolate the y so we can put it in slope-intercept form. X minus y equals 3. First thing we'll do is we'll subtract x on both sides, and then divide by -1, and we get y is equal to x minus 3. So let's graph that. -3 is our y-intercept. Our slope is 1. So we can go up 1, right 1, and continue that pattern as much as we need. And play connect the dots with the line. Then we'll graph the other one as well. First, put it in slope-intercept form. Isolate the y. Now we can see that the y-intercept is 1. The slope is 3, so that means we need to go up 3, right 1. Or we could do the opposite. We could go down 3 and left 1, down 3 and left 1, and then play connect the dots. And notice that those two graphs are intersecting at a coordinate. That coordinate is -2, -5. That means that is the solution to the system. So graphing can work, but it's tedious. It takes a long time to graph, and it's possible that the intersection is well off the Cartesian plane, somewhere in the very high negative numbers or maybe the high positive numbers, or it might be a fraction. And if it's a fraction, it can be really difficult to determine where those points are actually intersecting. So graphing works, but it's not the best method. There's much more efficient ways to solve a system. So we're going to focus on those other methods. Another method is using what's called substitution. we're going to solve one of the equations for one of the variables, substitute the result into the other equation, solve the resulting equation for the variable that remains, and then use the new known value to find the value of the other variable, and then we can check if we need to. So solving using substitution. Basically, you want to pick one of the equations and isolate a variable. Since there are 4 variables here, we have xy and xy, you technically have 4 ways to start this problem. But you want to work smart and efficiently. Which one of these is going to be the easiest letter to isolate? Again, you can start at any of them, but you want to pick one that's going to be easy to isolate. So I think the first one is going to be easy to get y by itself first. So let's do that. Let's take this first equation and isolate the y. That means I need to subtract 1/2 x on both sides. Now that we have isolated that y, we're going to take that expression and replace it in the other equation. So the other equation is x minus 2y equals 8. But what we want to do is we want to replace that y with what we know y to be. So we have x minus 2 times negative 1/2 x minus 2 equals 8. We simply replace the y variable with the expression from the first equation. And notice now we have an equation in one variable. That means we can find out what x is. So we'll distribute the negative 2. We get x plus 4 equals 8. 2x plus 4 equals 8. 2x equals 4. And x is equal to 2. So we now know what x is. Now we need to figure out what y is. Plug it back in. We know what y is. We know that y is equal to negative 1/2 x minus 2. So replace that x now. Y is equal to negative 1/2 times 2 minus 2. Y is equal to negative 1 minus 2. That means y must be negative 3. So we have our values for x and y. Let's write them as a coordinate. Remember that the answer is where those two lines intersect. They intersect at a point 2, negative 3. Elimination is another way to solve a system of equations. This one's probably one of my favorites to do by hand. I think it's better than substitution personally. Step 1, multiply both sides of one equation by some constant that will cause a variable term to cancel out. Step 2, add the two equations together and eliminate a variable. Step 3, solve the resulting equation for the variable that remains. Step 4, use the new known value to find the value of the other variable. And step 5 is to check. So in this example, our goal is to eliminate a variable by adding the two equations. Notice that you can't eliminate right away. If we added these two equations, 2x plus x is 3x, 4y plus negative y is 3y, the x's or the y's do not cancel. Sometimes they do at the beginning. Sometimes you don't have to do an extra step. But in this case, they don't eliminate, so we need to tweak one or potentially both of the equations so that when you add, a letter disappears. And again, you have options. You can eliminate the x's, you can eliminate the y's. It doesn't matter which one you do. I'm going to choose to eliminate the y's. Notice this one's positive and this one's negative. We just need to make this bottom one a negative 4, right? So that when we add, these y's will cancel. So I'm going to multiply the bottom equation by 4. So the top we're going to leave as it is. We don't need to change it. And we're going to multiply every term in the bottom equation by 4. So we get 4x minus 4y equals 16. Again, we're just distributing that 4 to each of these coefficients. And now notice what happens when we add these two equations. We get 6x, the y's cancel, that's what we wanted to happen. 6x equals 21. And then we can divide by 6, and we get that x is 21 over 6, or that reduces to 7/2. To find y, we're going to take our x value and plug it into one of the top equations that you start with. It doesn't matter which one, whichever looks easier. I think the second one looks easier in my opinion. So I'm going to take that second equation and replace x, in this case 7/2, up here. So we have 7/2 minus y equals 4. Subtract 7/2 on both sides, and we get 1/2. Divide, and we get y is equal to negative 1/2. And again, our final answer is a coordinate 7/2, negative 1/2. So if we graphed these two lines, they would intersect at the coordinate 7/2, negative 1/2. Next, we're going to do an application using systems. A math department has a limited budget to buy equipment. One teacher purchased 5 tablets and 7 calculators for $36.75. Another teacher purchased 7 tablets and 3 calculators for $42.95. Find the cost of 1 tablet and the cost of 1 calculator. So the first thing we need to do is actually create the equations. The first thing we know is 5 tablets and 7 calculators is $36.75. So 5 tablets plus 7 calculators is equal to $36.75. We also know that 7 tablets and 3 calculators total to be $42.95. And that's our system. This is our system of equations. We have options here. We could try to graph this, we can use substitution, or we can use elimination. Again, my preferred method, if we have to do it by hand, is using elimination. I think it's a little bit more efficient. Notice that right away we cannot add them. 5 plus 7 is 12, 7 plus 3 is 10. Adding these two equations right away will not help us. So we need to tweak one or both of the equations so that when we add them, one of the letters will cancel. And again, you have options here. You can choose to eliminate the x's, or in this case, the t's, or the y's, in this case, c's. So choose which letter you want to eliminate, t's or c's. In this case, let's say we want to eliminate the t first. If we want to eliminate the t, think about 5 and 7. What is their least common multiple? In this case, it would be 35. So we're going to have to multiply the top by 7 to get 35, and we'll have to multiply the bottom by 5 to get 35. But we need to make one of them negative because when we add them, we want them to cancel. It doesn't matter which one you make negative. I'll just choose to make the bottom negative. It doesn't matter. So now multiply the top right equation by 7. We get 35t plus 49c equals 25,725. And we're going to multiply the bottom equation by negative 5. Negative 35t minus 15c is equal to negative 21,475. And we want to add these. Notice that the t's are eliminated. They cancel. That's the whole point of this. We wanted them to be eliminated. And if we add the c's, we get 34c equals 25,725 minus 21,475 is 4250. Divide that by 34. and we get that C is equal to 125. That means each calculator cost $125. Now we just need to figure out what a tablet costs. And you can plug that C value into either of the first two equations. It doesn't matter which one. You'll get the same answer either way. I'm just going to use 5t plus 7 times C, which we found to be 125, is equal to 3675. 5t plus 875 is equal to 3675. Subtract the 875 and we get 2800. Divide that by 5 and we get that each tablet costs $560. Next, we're going to see some special situations when solving. First of those is an inconsistent system. An inconsistent system is one that has no solution. In a linear system, this occurs when lines are parallel. Picture parallel lines. They never intersect. So if you have parallel lines that never intersect, there's no solution to that system because they never cross. A dependent system is one that has infinitely many solutions. In a linear system, this occurs when the lines are coincident. That's just a fancy way of saying the same line. So looking at the graphs here, this is what we've been seeing. We've been seeing a system where the two lines intersect at a single solution. And for your homework and the test, quiz, this is what you'll see most often. But do be aware that there are other situations where the lines never intersect, therefore there is no solution. Or you could have two lines that are the exact same line, meaning they intersect an infinite number of times. If that's the case, we say that the solution, it has infinitely many solutions, or the lines are coincident. For example, let's practice using substitution and see what happens when we get one of those special situations. So if we're using substitution, we want to choose one of the equations and isolate one of the letters. Again, it doesn't matter which one you choose to isolate. There's 4 ways to start this problem. However, one of these equations, the first one, looks like it's going to be really easy to get y by itself. So let's do that. Let's isolate the y. Y is equal to negative 2x plus 5. And now we're going to take that value, that expression, and plug it into the other equation's y. So we have 4x plus 2 times replace y with negative 2x plus 5 equals 8. And solve. 4x minus 4x plus 10 equals 8. Notice the 4x's cancel. You're left with 10 equals 8. And in this situation, the variables disappear. If that happens, don't freak out. Sometimes, it can occur. When your variables disappear, you're going to be left with a statement. That statement is either true or false. You just need to ask yourself, what is it? In this case, this is a very false statement. So our answer is simply no solution. You may see 0 with a line through it. There is no solution to this system. And in this example, we're going to use elimination. Again, with elimination, you need to add the equations so that one of the variables disappears. Notice right away that this one looks a little different. Notice that the y is not grouped with the x like it has been in the previous examples. So let's first fix that. So the top equation we'll leave as it is. In the bottom equation, let's subtract 6y over so that it lines up nice with the other y variable. And now our goal is to add these equations so that a letter disappears. Right now, we cannot just right away add them. We need to tweak one or potentially both of the equations. And it looks like if I multiply the top by 2, the x's will cancel. So let's do that. Let's multiply the top equation by 2. 2x plus 6y is equal to negative 8. And now we'll just copy the bottom equation as it is. And let's add these two equations. 2x plus negative 2x cancels. 6y plus negative 6y cancels with 0. Negative 8 plus 8 is 0. And similar to the previous example, the variables disappeared. If that happens, don't freak out. Sometimes it can occur. If both variables disappear, you're going to be left with a statement. That statement is either true or false. In this case, this is a very true statement, right? 0 is always equal to 0. So that means there's an infinite number of solutions. And the reason it's an infinite number of solutions is because the lines are the same. They're coincident. They're intersecting each other at an infinite number of places. Now, the way we write our answer is going to be a little cumbersome the first time you see it. We're going to write the opening curly brace. We're going to say all x, y such that, and we're going to solve the equation, one of them, for a variable. In this case, we'll use x. X is equal to negative 3y minus 4. And then we'll put a comma, and then we have to define what y is. Y is any real number. And this big mess is our answer to this infinite numbers of solutions system.